Hello and welcome to Little Big Physics, a series in which we try to figure out the mechanics of the world of Little Big Planet from the ground up. Last time, we found that as objects move, something resists their movement, affecting lighter objects more than heavier ones, and we dubbed this phenomenon air resistance. We were able to produce a pretty accurate mathematical model for this effect, but we didn't make much progress towards understanding what was really making objects move differently. Today, we'll start our journey down a potential path to answers, but those answers won't necessarily come today, and we might not even be on the right track, but we won't know until we try. I'm going to latch on to a specific aspect of how we chose to describe air resistance. Air resists movement. Speaking from intuition, it seems that you can't alter the motion of an object in Little Big Planet without doing something to it. That something could be pulling or pushing it with another object, including sackboy or some kind of connector like a string or piston, gravity, or potentially this phenomenon that we call air resistance. How do you quantify a push or pull though? The most intuitive thing to do is to find a number that describes how strong a push or pull is. But what would that number be like? What unit would it have? For speed and density, we were able to determine what units to use by simply describing the property in words and translating that into units, like distance traveled over a given period of time or heaviness of a material for a given size. How can we do that with a push or pull though? The problem right now is that we don't really know very well what a push or pull does to an object. We know that it changes how an object moves, but how does it affect the object's movement specifically? It might be easier to think about this in a more concrete scenario. Suppose we have a ship moving through space, without any gravity at all. Its thrusters turn on and off every so often. We know that the thrusters will make the ship move forward, but how does the ship's speed change when the thrusters are on? What's the effect of turning the thrusters off? We want to be able to break this down into mathematical terms if we want to figure out what units to use for pushes and pulls. Let's start with a more direct approach. We want to produce a mathematical model for how an object moves when it does and doesn't receive a push. So let's record an object's movement as it is and isn't pushed. I've taken our reliable graphing apparatus back out again, and given it a block with a rocket to track. The block has an anti-gravity modifier on it, meaning that it won't experience any gravity, and its damping, something else that resists movement, like air resistance, maybe you should look into that one day, has been set to 0, so it should theoretically not experience any push or pull except for that of the rocket that's attached to. Just to be safe though, I'm going to stick to lower speeds so that air resistance has as small as possible of an effect, assuming it still applies to objects with modified gravity. Thus, I'll set the rocket to a very low power setting. I've rigged the rocket to fire it for a short period of time, then shut off, and then come back on again, so that we can show how it moves under each condition. The exact timing is the rocket being on for the first 2 seconds, off for the next 2, and then on for 1 more second, for a total of 5 seconds. I've also added another rocket on top, which won't do anything for now, just in anticipation of another test that we'll do in a minute. In any case, let's get this test running. Just like with the falling block back in the acceleration episode, I've transposed the results into Microsoft Excel. This time, however, I broke it into 4 sections, each corresponding to a period of the rocket being on or off, so that they can be compared. The initial results aren't quite as clear as they could be, but let's work the data a bit more to see if there's an emergent pattern here. Similar to when we graphed the falling block, we'll begin with the assumption that the acceleration is constant when the rocket is on, meaning that its speed increases at a constant rate. The type of equation that describes this is a quadratic equation, which is what we'll use to generate a fit for the green portions of the graph. Simply looking at the red portions, they look pretty straight, so let's guess that they're straight lines and use linear fits for them. The results of applying these fits are somewhat mixed. The linear fits actually seem to work quite well, for one. On the other hand, if the acceleration really is constant, then the number next to x squared on each green equation should be the same, since that's the magnitude of the acceleration. Furthermore, we can use some mathematical magic to find where the bottoms of these two curves are, which is negative b over 2a for those of you familiar with the quadratic formula. For the first curve, it's pretty much right at 0, which is where it should be if the block was stationary when the trial started. For the second though, it's actually way off to the right, at about 1 second, suggesting that the block was moving downwards at 0 seconds, which is clearly wrong. Let's not get too discouraged just yet though, since the second green portion is actually so small that the generated fit might not be very accurate. Let's look at the red portions more closely instead. The number next to x in the 2 red equations is how fast the block is moving during those intervals. you can see that it's moving at one speed for the duration of the first line, and then another faster speed for the duration of the second. Since there's nothing resisting the movement of the block, the speed that it travels during the red portions should be the same speed that it was traveling at the very end of the preceding green portion. Since we're assuming that the rocket provides constant acceleration, we can determine what that acceleration is by dividing the speed of the first red portion by the duration of the first green portion. This gives us about 5.79 lengths per second squared. Then, if the acceleration really is constant, we should be able to multiply this acceleration by the total amount of time it's spent accelerating, which is 3 seconds, to get the final speed of the block, which is its speed during the second red portion. Thus, we multiply by 3 seconds to arrive at 17.37 lengths per second, which compares with our graphed value of 17 lengths per second. I actually trust the fit of 17 lengths per second pretty well, since 10 points will define a line reasonably accurately, and the fit seems to match pretty nicely too. It's promising that our calculated acceleration is close to what the red portions imply, but there's the question of why our calculations slightly overshot the real speed. Since I had to transpose this graph onto a computer by hand, it's possible that it's just a slight error in the graph, but it's also possible that the small amount of air resistance at this low speed actually did lower the block's speed slightly too. In any case, it seems like we can throw away the fit for the second green portion since it's clearly incorrect, and cite insufficient data producing a poor fit as our reason to do so. What would a correct fit be then? Maybe the fit for the first green part would be, but let's try stitching the two green parts together and making a fit for that. I got rid of the red parts and translated the second green portion downwards, so that its first point would be where the first red portion's first point was. In theory, this is the trajectory that the block would have followed if the rocket never turned off. Generating an equation to fit this new graph gives us the equation shown, which has an acceleration between the two we saw before, and the bottom of the curve is about at 0, where it should be. It also looks like the generated fit has no issues with straying away from the data from 2 seconds onwards, which is where the stitched on portion begins, which is another good sign. Alright, that's one step in the right direction. A constant push on an object produces constant acceleration of that object. Having no push results in no acceleration, meaning that the speed of the object remains constant. What happens though if we vary the push? Does a push twice as strong produce twice the acceleration? I wanted to find an answer to this, but it turns out that there is a slight complication. One would assume that 50% thrust on a rocket is half as strong as 100% thrust on a rocket, whatever strong means in this context. Whatever it may mean, 0% thrust should mean no push at all, right? Strangely enough, that's actually not the case. A rocket set to 0% thrust and turn on will still move. That means that 50% thrust isn't actually halfway between no thrust at all and 100% thrust, as we wanted to assume. And since we don't actually have a way right now of knowing if this percentage scale is linear, we actually don't have a reliable way of producing one push with a rocket and then another with twice the strength. So we might have to call off this particular experiment until we can figure out a more reliable way of creating a push on a block. But we can try something else. What if we double the weight of what the rocket's pushing instead, to see what effect that might have? To accomplish this, we can simply copy the entire rocket setup and glue it onto itself. Despite there now being 4 rockets, the second pair won't fire at all, which will ensure that we're only changing one variable at a time. Just for the sake of variety, I also switched the second rocket ignition to trigger the top rocket instead of the bottom one, so that the block will speed up and then slow down. Here's what that looks like for the single block. Here's what it looks like for our new double block. Transposing these graphs into Excel kind of takes forever, so I'll just look at the footage for these ones. The single block traveled very nearly 50 lengths in 6 seconds. The double block traveled right around 25 lengths in the same amount of time. In fact, if you just stretch out the second graph vertically by a factor of 2, it looks just like the other one. This tells us that the double block was at half the height of the single block at any given moment, implying that it had half the speed, and thus half the acceleration as well. It looks like we can say, then, that there's an inverse relationship between the heaviness of the object being pushed and the rate at which it accelerates if it's given a specific push. At the very least, it's a single step towards defining the nature of pushing an object in LittleBIGPlanet. There's still just one more thing I want to look at though. While toying with the strength of the rocket, I noticed that if the block is big enough, and the rocket's strength is low enough, the rocket seems not to move the block at all, despite us knowing that it's producing a push. This actually contradicts the conclusion that we just made, since if you made the block 20 times heavier, that's just an estimate, not a real measurement, the block should theoretically accelerate 20 times more slowly, instead of just not accelerating at all. I think we'll have to put this question on the back burner until we've constructed a more complete model of pushes that incorporates heaviness, strength of the push, and anything else we find that affects what happens. It seems like today is another one of those days where we get just a hint of what's going on, but there's still a lot more work to do. Honestly, with how brief these episodes are, that's probably going to be the case pretty often. But this time, we have a concrete idea of where to look next, figuring out how to measure forces so that we can reliably test their effect on what happens in a given situation. Maybe we can have some fun along the way too. I think that trying to hit a distant target or something to that effect sounds like a nice way to put our theory to the test, but let's not get ahead of ourselves. For now, I'll see you guys next time. Stay curious.